Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And today we have another, as always, awesome hangout planned for you today. It turns out that the Milky Way has these very strange lobes on either side of it, and astronomers using Hubble have actually been able to measure some of the properties of these lobes using a quasar, and we're going to talk about some of the details with that today with one of the astronomers here. But before I get to the introductions, let me tell you, first of all, let me welcome my cohorts. With me, as always, is Dr. Carol Christian. She's the outreach scientist for Hubble. Hi, Carol.
Hello, hello.
And Scott Lewis, the driver of the internet extraordinaire. Hi, Scott.
Extraordinaire. It's getting longer. I
know.
This.
Yeah, it's better than
Esquire,
the third, I guess.
the
Or
third.
Esquire, yeah, Esquire the third, yeah. So we'd like to get your comments and questions throughout the Hangout. If you are so inclined, you can do that in a number of ways. The easiest, and my favorite way, is to use the Q&A app. But you can also comment on the event page in Google Plus that we are broadcasting from, as well as the YouTube page. We're looking at all of those comments as well. And finally, on Twitter, if you use the Hangout Hubble Hangout, Scott will be monitoring that and letting me know if there's any good tweets or comments that way, and we will read them out as they come or toward the end. So please interact with us. So joining me today is an astronomer also from the Space Telescope Science Institute, Dr. Andy Fox. Hi, Andy.
Hi, Tony. How you doing?
I'm good, thank you. Thank you for taking time out to join us. So you've made some pretty interesting measurements for us using Hubble. You have pointed it at a quasar that just so happened to be in a good spot to measure these very strange things that I guess only recently have been discovered, these features of our galaxy, these strange kind of lobe things, correct?
That is right. In fact, these lobes are called the Fermi bubbles, were only discovered in 2010 in their gamma ray emission by a satellite that NASA operates called the Fermi satellite. So really only in the last 5 years have we known about this new component of our galaxy, and we were able to use Hubble to measure how fast the gas was moving into these lobes, what that gas is composed of in terms of its chemical elements. And this was the first time we'd been able to really nail down some of these properties of the gas.
It's awesome, and I want to get to those measurements in just a minute. But Scott, can you put up that diagram that shows the Fermi bubbles? Fermi bubbles. Sorry. All right. So here's what they look like, or at least this is an artist impression of what they look like. Correct?
That is right. So what you can see here is the disk of our Milky Way. This is a side-on view of what our galaxy would look like from someone sitting outside. The disk of the galaxy comes across at a diagonal there, and those two purple lobes are centered on the core of the galaxy, the center of the Milky Way. You can see there is a lot of emission along the base of the lobes as you get closest to the center of the galaxy. And these things, they're really emitting light all across the electromagnetic spectrum. They were discovered in gamma rays. It turns out they also emit X-rays. They emit microwaves and radio waves. So they've started to be studied at all these different wavelengths. And we're piecing together the information we're getting from those different wavelengths to try and understand where they come from and what they're doing to the galaxy.
So, as you said at the beginning, this is we've known about these for about 5 years. Obviously, this is a vantage point that, sadly, we can never observe these things from. But we do have, you do have some of the images of these bubbles in the Fermi data, correct?
That is absolutely right.
Okay.
And in the Fermi data, you certainly see these two lobes. They look like balloons.
Scott, can you put those up?
Above and below the center of the galaxy. I'll just wait for those to come up. Yeah, here we are.
Okay.
Thanks, Scott. This is so this is an all-sky map. It shows the full night sky just as we're used to projecting, the surface of the Earth onto a map. We do the same thing in so-called galactic coordinates, and you can see right across the middle of this map, that's what we call the galactic equator. That's the disk of the galaxy where almost all the stars in our galaxy are located, is in that disk.
That's that bright band.
That's that bright band.
Okay, so let's talk a little bit about where is Fermi at when it's taking the. Is it in orbit above Earth? Is it somewhere in the solar? It's somewhere relatively close to Earth, correct?
Very close to Earth. That's right. So it's in orbit around the Earth, very similar to the way that Hubble is.
Okay.
So this is the image you get basically looking from the Earth, and this map is centered so that if you look towards the galactic center, that's right in the center here of the image, and you see those two orange-red lobes going out to either side, what we call the northern hemisphere and the southern hemisphere of the galaxy. They're not quite symmetric. There's a little bit more of the emission in the north than in the south, but you do see the same height extending into the halo of the galaxy in both sides. And this is the raw data that was actually discovered from that Fermi satellite that led to people dubbing them the Fermi bubbles.
Yeah, so these were first observed in gamma rays, and this is what our sky looks like in gamma rays. There's also the disk itself is very bright. You see a lot of photons there. What do the colors mean?
Well, it's color coded by the intensity, by how bright in gamma rays it is. But I should point out that the disk here, they've actually subtracted off the contribution from the disk, because the disk is glowing in gamma rays much brighter than the Fermi bubbles and the smaller.
So in order to see it at all, you have to subtract all that out.
They have to subtract off the disk, and that is actually quite a complicated process. They have to model how much it is. So this is a cleaned up map that you're seeing right here, which brings out the size of those Fermi bubbles.
Is that why those black areas there? Did that come out in the subtraction?
That's right. Yes.
Okay. All right.
Exactly.
So you subtracted out the contribution of the disk because it's so bright in gamma rays that you can't see these lobes. Now you can see the lobes, and what we have is we can see kind of a little map of an all-sky map of the in gamma rays. Are these other features like the ones that are like in the upper right part of the lobe there? Is that part of our galaxy, or is that background sky? Is that part of the lobes? How do you know?
Well, it's very hard to know. And actually, that's an open question. As you go up into the northern Fermi bubble, you keep going to the north. You do see that orangey region, and that some of that may be associated physically with the Fermi bubbles, but some of it could be in the foreground. I mean, there are spiral arms of our galaxy between us and the galactic center, and those spiral arms can blow up material. They can blow gas into the halo, which can also end up giving you X-ray emission and gamma ray emission. So it's actually very hard to tell from a map like this what is very close to the galactic center and what is somewhere else. But as we'll get into, that's where the Hubble data is actually very useful, because Hubble is able to look at this from a different perspective, from a different angle, with its different types of data, and that can give you more information about where things are.
So based on this image, all we know is where it's bright in gamma rays. We don't know how far away it is, or where, any location information.
You got it, exactly. All this is total intensity. So it's you've got to be careful with this alone, what you really understand and what you don't.
Okay, you also took we also have images in other wavelengths, don't we?
That's correct.
Wait. So I have a question. So that loopy thing off to the left, what are those loopy things? Have you figured out what those loops are?
Are you talking about to the far left of the image here?
No. In, up, down. That
we
loop.
are so
That
high
loop
tech
thing
here.
there.
Yes, got it. Again, this could be related to the southern Fermi bubble, but it's not a definitive connection. We don't know for sure that is at the distance of the galactic center versus something that's in the foreground.
Right.
Yeah.
Just very suggestive. Okay.
Yeah.
Thanks.
That's right.
So we saw these things in gamma rays, and then we looked at it in other wavelengths. Scott, you want to put another one up? There we go. Here we are in microwave and radio, and they're really bright in there too.
That's right. Now this is a microwave image, and the sharp-eyed viewers looking at this will notice that this is actually from 2004, which is before the Fermi bubbles were formally discovered. Okay, this is from a paper that came out in 2004. The reason for that is there had been this glow above and below the center of the galaxy in microwaves, but no one was really sure whether that was a real signal or whether it was something to do with the way that you subtract the disk. Because just like with the last image, you can see the black band in the middle here. That's where the disk of our galaxy emits microwaves, and that has to be subtracted off. So there was a hint of something going on in the microwave data from 2004, but when the gamma ray data came out in 2010, then it was bright in the same regions. We have the lobes both in the north and the south. Then because you're seeing the signal at totally different wavelengths, people really believed it and knew that that was a genuine structure that they had detected.
Okay, so since this is a relatively new discovery, do we know anything else about? Do we know why they're there? I mean, are these lobes a common occurrence in galaxies?
So those are two very good questions. On the first one, why they're there, we have two basic ideas of where they are coming from and what is powering them. And they're both to do with the center of the Milky Way, because we know that the center of the galaxy is a very energetic place, and we know there's a supermassive black hole there with a mass several million times as high as the sun's mass. So one possibility is that that supermassive black hole at the center of our galaxy is accreting matter from its surroundings, and after the gas accretes towards the black hole, it gets ejected and blown out into the halo. And that blowout can create these bubbles. Another possibility is that...
But only when it's blowing out, right? Because right now, for example, it's not really eating anything up. So it's
That's
pretty
right. So only when it's active, yeah,
Okay.
because we know that black holes have active phases or not active phases. So if it's actively accreting gas, then it would be driving stuff out into the halo. If it's in a quiet phase, it wouldn't be doing that. So that's definitely a stop-start episodic type of event. So that's the black hole theory. The other idea is whether star formation can be driving these bubbles into the halo. So when you get star formation happening at a very high rate, in other words, lots of stars forming, lots of stars running out of fuel, some of them will turn into supernovae, and supernovae can explode and drive gas out of the disk of the galaxy up into the halo. And we know that there are a lot of very massive stars close to the center of the galaxy because they've been observed. So it could be that those massive stars near the center of the galaxy have been turning into supernovae, blowing bubbles out into what is now called the Fermi bubble.
So
we're not sure which of those two it is that is actually dominating.
But most of the rapid star, or the active star formation in our galaxy, isn't it going on at the leading edges of the spiral arms mostly? And is the center of the galaxy high activity in starbirth?
It is. There's a lot of starburst activity in the nucleus of the galaxy. Just as there also is in the spiral arms, as you say. But if you look at how much star formation is going on, like per unit area of the disk, it's very high near the center of the galaxy, and that's the number that you want to be high to be able to drive out a wind. Okay,
I think we have one more slide in another wavelength. Is that true?
Actually, it's just this one.
Okay. So I wanted to make sure I got all the wavelengths that we had. So. And again, the black band across there is the subtraction of the disk of our galaxy in there. That doesn't, so that you can actually see these things, because the signal from the disk is so strong. Correct?
It is. And so it's really a contrast thing, because if you put on that disk emission, it would be so bright that everything else in the background would be lost in the noise.
Okay, so I have a question from Seb Dustbunny. I'm going to go ahead and read it. It's a little bit ahead of where I wanted to be, but he goes, has evidence of these bubbles seen in other galaxies, and does it require a side-on view? So that goes back to my question, how common are these? Do you have any sense of, have these been seen in other galaxies at all?
So as far as gamma ray bubbles go, the answer is no. We don't have any cases of other galaxies where we've seen these. The problem is that we're not sensitive to detecting the gamma ray emission from other galaxies. In other words, the reason we're not seeing them is not necessarily that they don't exist, but it's that the light would be so faint that our telescopes aren't able to detect it and say whether it's there or not.
So our gamma ray telescopes aren't powerful enough. That's what you're saying.
That's another way of saying it. So the Fermi satellite is sensitive enough that it can see these bubbles in the Milky Way, but even then it took this very careful job of subtracting the emission from the disk and a lot of processing to do that. So that was a very challenging discovery, even in our own Milky Way. So when you go to another galaxy, which is much further away, so the emission is much fainter by the time it's got to us, it's so challenging that we haven't been able to see them.
But even is that true even for the more nearby galaxies? I mean, the last part of his question is, or could imaging this in Andromeda be tried? Could you see this maybe in a close galaxy like the Andromeda galaxy?
You could try this in X-rays in Andromeda, certainly in radio waves. So in other wavelengths, it's certainly true that we've seen extended halos and even bubble-type structures in galaxies and galaxy clusters. So particularly radio waves. People have studied bubble structures in radio waves in other galaxies for some time. But the gamma ray part of it, and that's what led to this Fermi bubble name, really at the moment that's our own galaxy. And even Andromeda, the closest big spiral galaxy to the Milky Way, would, if it had Fermi bubbles that were the same size as the Milky Way, they would be too faint for us to see with our current telescopes.
Got it. Okay, thanks, Seb. That was a good question. And so it would seem to me, like you said, there's two prevailing theories about what's causing these things, and one of them was the black hole, our supermassive black hole in the center of our galaxy. I wonder, wouldn't there be, and of course there are active and inactive periods of that black hole. Don't you think that would have a characteristic pattern to it, to these bubbles, if it were sometimes being contributed to by a black hole jets and other times not? Do you understand what I'm asking?
Yeah. So
wouldn't you expect to see some kind of, I don't know, rings or patterning to the bubbles?
Yes, I see what you're saying. So we happen to have observed the bubbles as they are right now. So our work with the Hubble telescope has actually given us an age of how long has it taken the gas to flow out from the center of the galaxy to where we observe it in this outflow, where it's feeding the Fermi bubbles.
Okay.
And that age is about 2 or 3 million years. So what that's saying is that 2 or 3 million years ago, there was an event at the galactic center which blew out material, and it has currently reached where we see it on the sky. If someone was to come back in another 2 million years from now, or whatever number of million years, and observe it, they would find the structure has got to a different stage. So we're only looking at it at one point in time. That's the difficulty. If we'd been able to chart how it's changing, then we could really see how often is it expanding, or is it going to reach some sort of maximum size.
Okay.
We're just limited by the fact we can only see it right now at the current time.
Got it. Okay, that's good. So let's get to your measurements then. So you looked at these bubbles in a very interesting way. It turns out there was a quasar that happened to be in a certain location that was very fortuitous. Why don't you give us the background of the observations that you made?
Sure. So if we can pull up the slide to help show this, that would be great.
Oh, that's right. There's a schematic. If you could do that, Scott, thank you.
What we've been doing is thinking about how to use the Hubble telescope to study these Fermi bubbles. And here you can see this is another side-on view of what these things would look like from outside the galaxy, and the Hubble telescope is over there in the disk on the right. Now, we identified quasars, that is very bright sources of radiation that happen to lie behind the bubbles. So there's the sight line in yellow towards a bright quasar, which in our case was just at the right place of the sky. It had the right coordinates to lie close to the bottom of the northern Fermi bubble, right, one of the two bubbles. And what we can do is we can take the light from this quasar, in fact the ultraviolet light, which Hubble is sensitive to because it's up in orbit above the Earth's atmosphere, so it can make measurements all the way down into the ultraviolet, which you can't do from the ground. And by analyzing that ultraviolet light, we can say something about the outflowing gas in the Fermi bubble. And the reason is that outflowing gas leaves its signature in the ultraviolet light. It leaves a signature in which frequencies of light, which colors of light are absorbed and taken out of the spectrum. So we do what we call a spectroscopic analysis, and we measure lines of certain elements, spectral lines, which appear in the ultraviolet. And that's a way of measuring the properties of the gas that's in these bubbles. And that was how we were able, for the first time, to measure what is the velocity of the gas coming out of the Milky Way's nucleus into the Fermi bubbles. And we were also able to say something about what's its composition, so which elements are actually present in that gas, because that also gives you a clue about where these things came from.
Okay, let's start with what they're made of first. What did you discover? What are these clouds made of?
So the elements that we detected are silicon, carbon, and aluminum. Each of those elements has several of these spectral lines that fall in the ultraviolet that we can measure, and we can see how much of these elements are present in the gas.
Sorry, do you have the spectrum on the?
Yeah, I was just going to say.
Visualization. It looks like it's not okay.
Yeah, there it is.
All right, okay.
Yeah,
it's actually on the image that is in
Yeah.
the press release, but we can use this one.
Okay, so this is the sort of data that we really work with when we get down to the details of analyzing the Hubble data. This is the spectrum which shows intensity, or how much light there is, against velocity along the line of sight. And this is for a particular line. This is twice ionized silicon. It's silicon atoms that have had 2 electrons removed from them. That gives you a feature at a very certain wavelength in the spectrum, and we know exactly where that is in the spectrum, so we know where to look. What you see here is different components, and those components are shaded in different colors. There's one shaded in blue at negative velocities, 2 on the other side at positive velocities in yellow and in orange. What this is telling you is it's basically using the Doppler effect. The component that is shaded in blue, that is moving towards us. It's what we call blue shifted, right? It's gas that is, we think, on the near side of this outflowing cone of gas that comes out from the galactic center. The yellow and the orange components are redshifted. Their light has been shifted towards the red, and that's what you get from the far side of the outflow, which is on the other side of the galactic center. So just in this one sight line, we can see these gas components, some of which is coming towards you, some of which is going away from you. And that's exactly what you get from one of these nuclear outflows that comes out in a cone-shaped pattern.
And so the silicon, I'm going to get to the speeds and the velocities in just a minute, but I want to go. What does the elements themselves telling you? Does it give you any information about what their source might be? What might be causing these?
Well, it does give you information, but unfortunately, it's not conclusive in telling you if it's the black hole or the star formation.
Okay.
So the silicon, the carbon, and the aluminum, we do know that those elements are all produced in stars, in star formation. They get forged in the cores of massive stars, and they eventually do get released. But what you don't know is how long ago that happened. So it could have been that these elements are produced in stars, they're released into the space between stars, and then some of that gets accreted onto the central black hole, or it could have been that they just get blown directly out from the supernovae.
Right,
so in other words, it doesn't really tell you for sure whether it's the star formation model or the black hole model, but it does tell you that at some point this gas was processed through star formation. It's giving you these clues to its origin.
So the jury's still out. There's just not a conclusive fingerprint here in just the spectrum itself, just the elements themselves.
Right.
So, but I want to get to the velocity now and talk. So, but before I do, the Doppler effect that you're talking about, let me just try and see if I can give a little basic background on this. If you take a spectrum of an object at rest, you will see certain lines, dark and bright lines, appear at very specific spots in the spectrum, depending on what the element is. And if that thing is moving, whatever it is you're measuring, you will actually see all of those lines shifted one way or another, and it will be shifted. How much it shifted gives you an idea of how fast it's going, and which direction it shifted tells you whether it's coming towards you or away from you. So that is how the Doppler shift is used in spectra, and you can see it in this graph here.
Right. So the dotted line that goes horizontally is essentially the ambient intensity, and the light comes from another source and hits silicon atoms and is absorbed, and so that central line is most of the silicon. But if that silicon atom is moving, and in case many silicon atoms moving or sort of in a bulk motion, light has to, when it's absorbed, is shifted, either if the material is moving towards us or away. And our analogy is always the train whistle. You hear a high pitch the neutral tone, and then the low pitch as a train goes past you if it's blowing its whistle the whole time. So that's also how speed radar works. So I actually once got out of a ticket because I explained the Doppler effect to a cop because he didn't know how it worked, and he gave me a warning because I had given him a physics lesson. But anyway, I wouldn't try that at home. But anyway, but that's
saved
how
by physics.
Yeah, really. So that's how they tell that the material is moving, because there's nothing else absorbing in that region except the silicon.
Good. So now, Andy, why don't you tell us a little bit about these speeds then? You've got them at more or less going out at about plus or minus 200 kilometers per second, right?
That's right. So these velocities are what we measure along the line of sight. So in other words, when you look towards this quasar, which is close to the galactic center, the blue stuff is coming towards you about minus 250 kilometers per second or so. The orange component is plus 250 kilometers per second. But what we have to do is we have to realize that we're just seeing a projection along our line of sight of the outflow, because our understanding is that most of the gas is moving directly out from the galactic center, so up into the halo of the galaxy. What you see is the projection of that onto our line of sight. So we have to do a little bit of geometry to determine what is the outflow speed, the total velocity of the gas that moves away from the center of the galaxy, because that's not the same as what we see along our line of sight.
I don't understand. So this is a measurement of one specific path that the quasar went through. So you know about the gas right there.
You do.
And what did you do now to figure out the rest? I don't understand.
Well, so you're measuring along that line of sight towards this particular quasar.
Right. You have that one data point.
Right, whether these components are coming towards you or away from you. But in reality, this gas is moving in 3 dimensions, not just in 1 dimension towards us or away from us. So we have to do some geometry to determine how fast is it actually moving directly up. If you imagine you're looking at that side view of the galaxy again, the direction that this outflow is going is out into the halo, up above from the galactic center. So what you were seeing in the spectrum is the component of that is along your line of sight. So there's just an extra stage that goes into our calculations that goes from our line of sight velocity to what is the actual outflow velocity in 3 dimensions, which is how fast is the gas launched from the galactic center. Because that number is much faster. It's more like 900 or 1,000 kilometers per second.
Wow, that's really fast. So there's a related comment and question here from Adam Synergy, and I wanted to highlight this. He's going, so this observation is just the beginning, right? Surely you will need to repeat this many times with different background quasars to fully map the Fermi bubbles. And you're saying there's a technique here for getting that information.
Yeah, no, that's a very good question. We do need to do that. We began our program with this one sightline because it just happened to lie in such a great place. This is the best quasar we have in terms of being close to the galactic center where the wind is going to be strongest, because whatever is producing this, it's something to do with the galactic center. It's either stars near the galactic center or it's the black hole at the galactic center. So we were looking for targets as close as possible to that point. And this was the best quasar. But our full sample is more like 20 or so quasars, some of which are inside the Fermi bubbles, some of which are just outside. And we have the ongoing task right now of analyzing all that data and measuring the absorption lines that we see with just the same techniques we've been talking about. We need to do that for the full sample, not just this one case.
Good. Good question, Adam. Thank you. And Craig Landon, I'm going to get to yours in just a minute. But so the measurements you've got tell you a little bit about how these things are moving fast, by the way. These things are really moving out there. And you said something earlier about this happened, what was it, 2.5 million years ago, or whatever it was that caused, and is the way you found that out by running the clock backwards, going backward, and you know how fast they are right now, so you just figured out to get where they are now, it must have taken them this long?
That's exactly right. That's the calculation we did. We measured the outflow velocity and found about 900 or 1,000 kilometers per second. That's about 2 million miles per hour in more familiar units.
Yeah.
Million
miles an hour.
2 million miles an hour gushing out from the galactic center. And because we know how far from the galactic center it's reached, we know the distance, right? So we've got a distance, we've got a velocity, we can turn back the clock and figure out the time.
Right.
And when you do that calculation, the answer is somewhere between 2.5 to 3 or 4 million years. So it tells you that that's how long it's taken for the gas to be driven away from the galactic center to where we see it. Or to put it differently, it just tells you that 2 or 3 million years ago there was a very energetic event. There were some fireworks, something happened that was capable of driving this stuff out, producing what we now see.
And Scott's got a very France-friendly looking schematic up here to sort of show what we've been talking about all this time. You can see where the red and the blue areas of the spectrum are in the little diagram in the lower left, and so it gives a sense a little bit more of what we were just talking about. But this is more of an artist representation of that, where the other stuff was actual. And the other stuff was actual data. So, okay, so let's see. Let me get to Craig Landon here. He's got a question here for us that is, what might be the contribution of gravitational waves to what can be inferred from the views in different wavelengths? So, can gravity waves affect these in any way from what you've seen in the different wavelengths? Or is it too early to tell?
I think it's too early to say what the contribution of gravitational waves would be. If there was a place where that would be relevant, it would probably be very close to the center at the black hole itself, where you have a several million solar mass object, which is certainly going to be disturbing the space-time around it. But we don't see what the connection would be right now between these observations and gravitational waves.
Cool. Thanks, Craig. So, how do we know how hot these things are? Do we know how the temperature of the gas?
Well, the gas that we're seeing in the Hubble data, it's actually not that hot by astronomers' standards. It's probably around 10,000 degrees Kelvin, which is 17,000 Fahrenheit or so.
That's pretty hot.
It's pretty hot by our everyday standards, but in terms of like interstellar space, that's not so hot. There's plenty of stuff which is at 1 million degrees or 10 million degrees or hotter.
Right, and it's also not very dense, right? I was going to get to density too while we're talking about temperature. Are these very dense bubbles?
Not really. I mean, the typical densities you have in these things are something like 1 atom per cubic centimeter, which are extraordinarily low by our standards on Earth, but that's the sort of number you come across in the interstellar space. But the interesting thing about the temperatures, if I can just come back to this point, is
sure.
People have been studying winds coming out of other galaxies. And they haven't been able to see the bubbles because of what we talked about, and the gamma rays are too faint. But they have been able to see winds. And when they studied winds, it's widely accepted that most of the wind and the energy that comes out from the center of galaxies is very hot, where it's extremely hard to detect. So it's possible that what we're seeing in this cooler gas with the Hubble data are just small clouds that are being taken along for the ride in the outflow. We're not really seeing the bulk of the mass, the bulk of the energy in the wind. We're just seeing small pockets of material that are relatively dense and are being taken along for the ride.
Now this is really interesting. I hadn't heard this. So galactic winds, describe what those would be like. I'm having trouble visual. Is it the entire galaxy blowing out gases?
It could be galactic-wide winds. I'm focusing here more on the galactic nuclear winds.
Okay.
But if you look at the supernova model, where it's the supernova that are powering the outflow, those explosions heat the gas to extremely high temperatures, well over 1 million degrees. That is the type of gas that can expand and blow a wind out into the halo. So you could think of that as the real hot wind, and the little cool clumps that we see, they're just catching a ride. They're just surfing the waves up into the halo. But this is the interesting thing. So we're not really seeing all of the gas by any means. We're just seeing the small clumps that are at the right temperature that Hubble can see them. Because for all the wonderful things that Hubble can do in the ultraviolet, it can't actually measure the really hot million-degree phase. That is where theorists think most of the wind, most of the energy is being carried.
Okay, so what's confusing about that to me is that we can see these winds in other galaxies, but we can't see it in our own?
We can see winds in X-rays. The one thing we can
in our galaxy or in distant galaxies?
Well, both.
Okay.
But the difficulty in our own galaxy is that you've got this problem of being able to see the forest for the trees, because we're right here in the disk of the galaxy.
Okay, I see.
We're rotating. There's a lot of foreground material right between us and the galactic center. So ironically, it's actually harder sometimes to figure out what's going on at the center of the Milky Way. Then you look at another galaxy. It's further away, but you've got a clean shot at it. So you don't have all the foreground issues to deal with.
Okay, so it's the same problem you have with seeing the bubbles at all. We got so much. Our galaxy is so bright that it's in the way of seeing these winds in any meaningful way. So we have to see.
Yeah.
Okay.
Exactly. Right.
Okay. Well, so we have another comment here from Filippo Conti. Is it possible that the event horizon is something like a sphere, and so the bubbles are just formed by materials that are going towards the horizon from both sides? I guess that's more of a geometry of the black hole contribution question.
Right. That's an interesting thought. So if the Fermi bubbles are being powered by the black hole, then of course nothing can escape from the event horizon of that black hole, but you can get material which escapes from the region just around the event horizon. So if we have this accretion disk, which is where the gas gets really hot and is falling towards and swirling onto the black hole, that's the region where you can get outflows that drive into the bubbles. Maybe even jets as well. We haven't talked about jets, but there is one theoretical model which says that you can drive these jets out from the supermassive black hole, and that is what is contributing towards the Fermi bubbles.
Oh, okay, that's right. So that would be these high-energy jets that are in very active galactic nuclei or black holes.
That's right, and you see these jets around other active galactic nuclei, other galaxies, exactly. But they would be formed somewhere fairly close into the center of the black hole, but still outside the event horizon.
Oh, okay, good. That was a good question. Okay, so, all right, so...
I have a question. So I may have missed this, but so there's this bubble, but so it's the waist, if you will, is tight, at least the way you have detected it, is tight near the plane. There still is emission within the plane of the galaxy caused by the same sources, right?
That's right, yes.
It's not necessarily, it could be, but not necessarily bipolar like that. Is that right?
Yes, that's right. So that waist is telling you something important, because what we think is happening is that the Fermi bubble, however it gets created, it has to expand into something. And the denser the material that it expands into, the harder it is to get bigger. Whereas the less dense, the easier it is to expand. So naturally, the bubbles just inflate and get bigger away from the galactic center in the vertical direction. But in the waist direction, sort of towards the sides, they're probably encountering a lot more resistance because there's a lot more gas there. There's a lot more interstellar material, and that's what's confining the bubbles. And we think that that's where the waist structure, the shape of these things, comes from. It's sort of set by what is restricting the
stuff that's in the way.
Right, and we can't detect that way. I mean, we can detect that way, but in the plane, we can't do this observation because there's all this other stuff there.
Yeah, besides, we go through a lot of trouble to subtract all that out anyhow. So.
Yeah, right, exactly. So it would be a tiny little, if we could see it at all.
Okay, so Red Hot Bagel is asking, this might be a dumb question. No such thing on our Hangouts. Thank you for asking.
Actually, it's a really good question.
It's actually not a dumb question. But how exactly do you measure the temperatures of these gases? How do you measure?
Not a bad question at all. We have access in the Hubble ultraviolet data to different lines. I showed a line earlier on when we had a graphic up of twice ionized silicon. So a silicon atom that's being ionized had 2 electrons taken out of it. Now the level of ionization, so how many electrons it's been removed, tells you something about the temperature, because the hotter the gas, the more electrons will be removed from all the atoms. Whereas if the gas is very cool, the gas can be atomic or even molecular. So twice ionized silicon, the one that is shown in that particular graph, just happens to live in interstellar gas at temperatures of approximately 10,000 Kelvin.
You'll have to describe for us twice ionized. What do you mean by that?
So that means
It's
two
been
electrons.
ionized twice. I mean,
Yes.
come on, Tony.
It means 2 electrons have been taken out of it. So if you start with a neutral silicon atom,
Thank you.
you take 2 electrons out, you're left with what we call one of these twice ionized silicon atoms, and that leaves its imprint at a certain wavelength.
Good. I just wanted to get that clear because a lot of people, it's not clear what, the word ionized is a big one, so I want to make sure we explain
So
what that is.
it's not a very, very big, long thermometer that we shove out there. We have ways of using the light to actually get the information in the spectra to actually find out what's going on in those gases and in those ions that's going on.
That's right. And these ions each live at different temperatures. So that's the short answer, is that this one lives at approximately 10,000 Kelvin, but it's certainly not a very precise number.
Right.
It could be 8,000, 10,000, somewhere in that ballpark.
Thank you, Red Hot Bagel. That was a good question.
It was a very good question.
So we touched on this briefly earlier, and I want to follow up with you're looking at other quasars. I want to talk about what's next. What's the future here? What do you have coming up for us in terms of learning more about these Fermi bubbles? Do you have anything planned?
So we do. We have the other quasars. As I mentioned, there's about 20 of them that we have. We've got the data. It's just a question of analyzing all these lines and modeling the outflow. We also have some stars. So it turns out that the Milky Way is cooperating, and it gives us some halo stars, which some of them actually are in the Fermi bubbles. And this is really interesting because you think of these Fermi bubbles as these very energetic places, but there are these single stars that happen to live in the halo of the galaxy, not in the disk, but up there. And we know how far away they are.
These are just errant stars that happen to be up above the plane of the galaxy.
Yep, they're just wayward, and they've wandered up there, however that their history did that to them. But we can use them and do the same experiment. But now, the difference with these stars is that because they're in the Fermi bubble, you're only seeing half of the outflow. You're only seeing the part of it which is on the near side.
Right.
Whereas when we do the quasar experiment that we've already done, you can see all the way through the full path of the outflow. So you can see the front side of it, and you can see the back side of it. So,
but still, that's better than nothing, right? That's more information than we have
absolutely,
before, especially for the near side. Right.
Yes. And there are 1 or 2 cases where we have a foreground star, which we believe is in the Fermi bubbles, and a background quasar, which is very close to it on the sky. So we can compare the absorption.
Oh, that's nice.
Compare the spectrum, and so we can say something about, well, if we see this feature in one sightline and we don't see it in the other one, that gives us some information about where it is in distance.
Physically, yeah.
So when you get, not that I want to push you or anything, but when are you going to get all that's done and come back and tell us what you found out? Is there a timeline?
I'm confident that we can make some good progress on that within this year. I've got a great team of people working with me on this project, people focusing on modeling. We've also got some radio data which gives us a new set of observations on how much neutral gas there is that goes along with this ionized stuff.
Radio data from ALMA?
This is actually from the Green Bank Telescope, which is in West Virginia.
Oh, okay. That's old school.
It's old school, but it's a fantastic facility. It's
been around a long time.
Well, this is a huge single dish telescope, and it provides very, very deep observations. So for what we needed to do, it's as good as we could get.
When my friends went to UVA and she was working out there, and she's like, no cell phone zone, don't bring anything like that.
Right.
That's a big thing to think about, because when we're talking about these wavelengths of light, that's what's going on with our everyday gadgets, is that is light and it's going to be interfering. So this place in Virginia, it's completely, when you're thinking about light preservation as far as dark skies, well, we have to do the same thing with these types of telescopes to make sure there's no interference from these longer wavelengths of light as well.
It's the radio equivalent of shining a flashlight down the tube or something.
Right.
So, okay. So Scott, have I missed any? Is there any Twitter things that
There's a bunch of tweets, a lot of retweets going on. There is Astro Gingersnap, also known as Amy Lynn. It's like, I think my head might explode right now. from all the awesome space news today on Rosetta and the Hubble Hangout and Vesta. So we are adding to her mind explosion of all the science.
Great.
And Francis Reddy also shared out the NASA video release, which I have put into the Google Plus event page. So I have linked to that, and it's really good. It's a really good animation showing the Fermi spacecraft and also the animation going on too, as far as explaining what's going on with the with these Fermi bubbles.
Excellent.
Yeah,
so I have a question. So in principle, if you were given Hubble Space Telescope, you could do a whole bunch of sight lines then, all over the place, and then you'd want to repeat that periodically just to see what the changes are, right? So you could map the whole thing and then see how it changes. Is that right? Do I get that?
In principle, yes. The problem is actually the timescales that you would need. So if I or my colleagues could live to like 2 million years, then that's the sort of time we think we would need to see these things actually change on the sky.
But you could do different sight lines.
You could. That's
in a year. Yeah, right.
So you would look for other quasars that happen to lie close to the galactic center and do the same thing. We got really lucky with this one quasar because there's a lot of dust. What we call dust, it's like interstellar particles that block the light from background quasars, especially when you get close to the galactic center. It just happens there's like a little window through the low halo of the galaxy, and this quasar is in that window. But other places nearby have so much dust that the light doesn't get through, which means you can't find the quasars you need to do this type of experiment. So it's hard, but we have to really push down and find very faint sources to do this. So it can take a lot of time, a lot of observing time on the telescope to get this done.
Pesky dust. We gotta get a vacuum cleaner out there and clear it out of the way. All right. Well, so Dr. Andy Fox, I want to thank you very much for joining us in our hangout. Will you come back later once you've got more data?
Sure, I'd be happy to. Yeah.
Awesome. Good. Look for an invite because I want to follow up on this and learn more about it.
Here's a final slide. I did also put the link out there. I'm about to put up on Twitter here in a bit, but if you want to read more about the paper that goes on here, I have linked it into the Google event page. I'll make sure it gets put up onto YouTube, and I'm just about to tweet it out. But you can go to archive and take a look at that paper as well if you want to do a little bit deeper digging into the science that's there.
Good. Yes. Thanks for reminding me about that. So if you want to read the actual paper, there's a link to it as well as the link to the press release on hubblesite.org to learn more as well. So that's it for this week, everybody. Next week, Carol, Scott, and I will be meeting we have another in our series of Hubble 25 Hangouts to celebrate the 25th anniversary of Hubble. We'll have Carolyn Collins-Peterson with us to talk more about the illustrious history of Hubble, and as we said the last time we did a history of Hubble hangout, we're going to be doing many of these. So because 25 years is a long time, a lot of stuff happens. So we'll have her next week. We hope you'll tune in and check us out. I'll create the events tomorrow, and I keep getting phone calls.
That is an amazing ringtone, though.
All right.
Are you going to the danger zone?
Yeah, really.
Danger zone. I forgot that during
really.
Okay, everybody.
I was gonna have a fun night, but you apparently you always have a fun night with that ringtone.
Yeah.
That's right.
Really.
Danger zone. Okay, everybody. Thank you guys for watching. We'll see you guys next week. And as always,
keep looking up.
There you go.
Okay.
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And today we have another, as always, awesome hangout planned for you today. It turns out that the Milky Way has these very strange lobes on either side of it, and astronomers using Hubble have actually been able to measure some of the properties of these lobes using a quasar, and we're going to talk about some of the details with that today with one of the astronomers here. But before I get to the introductions, let me tell you, first of all, let me welcome my cohorts. With me, as always, is Dr. Carol Christian. She's the outreach scientist for Hubble. Hi, Carol.
Hello.
And Scott Lewis, the driver of the internet extraordinaire. Hi, Scott.
Extraordinaire. It's getting longer. I like this.
I know. Yeah, it's better than
Esquire,
the third, I guess.
the
Or
third.
Esquire, yeah, Esquire the third, yeah. So we'd like to get your comments and questions throughout the Hangout. If you are so inclined, you can do that in a number of ways. The easiest, and my favorite way, is to use the Q&A app. But you can also comment on the event page in Google Plus that we are broadcasting from, as well as the YouTube page. We're looking at all of those comments as well. And finally, on Twitter, if you use the Hubble Hangout, Scott will be monitoring that and letting me know if there's any good tweets or comments that way, and we will read them out as they come or toward the end. So please interact with us. So joining me today is an astronomer also from the Space Telescope Science Institute, Dr. Andy Fox. Hi, Andy.
Hi, Tony. How are you doing?
I'm good, thank you. Thank you for taking time out.
Across the electromagnetic spectrum, they were discovered in gamma rays. It turns out they also emit X-rays. They emit microwaves and radio waves. So they've started to be studied at all these different wavelengths. And we're piecing together the information we're getting from those different wavelengths to try and understand where they come from and what they're doing to the galaxy.
So, as you said at the beginning, this is we've known about these for about 5 years. Obviously, this is a vantage point that, sadly, we can never observe these things from. But we do have you do have some of the images of these bubbles in the Fermi data, correct?
That is absolutely right.
Okay.
And in the Fermi data, you certainly see these two lobes. They look like balloons.
Scott, can you put those up?
Above and below the center of the galaxy. I'll just wait for those to come up. Yeah, here we are.
Okay.
Thanks, Scott. This is this is an all-sky map. It shows the full night sky, just as we're used to projecting, the surface of the Earth onto a map. We do the same thing in so-called galactic coordinates, and you can see right across the middle of this map. That's what we call the galactic equator. That's the disk of the galaxy, where almost all the stars in our galaxy are located, is in that disk.
That's that bright band.
That's that bright band.
Okay, so let's talk a little bit about where is Fermi at when it's taking. Is it in orbit above Earth? Is it somewhere in the solar? It's somewhere relatively close to Earth, correct?
Very close to Earth. That's right. So it's in orbit around the Earth, very similar to the way that Hubble is.
Okay.
So this is the image you get basically looking from the Earth, and this map is centered so that if you look towards the galactic center, that's right in the center here of the image. And you see those two orange-red lobes going out to either side, what we call the northern hemisphere and the southern hemisphere of the galaxy. They're not quite symmetric. There's a little bit more of the emission in the north than in the south, but you do see the same height extending into the halo of the galaxy in both sides. And this is the raw data that was actually discovered from that Fermi satellite that led to people dubbing them the Fermi bubbles.
Yeah, so these were first observed in gamma rays, and this is what our sky looks like in gamma rays. There's also the disk itself is very bright. You see a lot of photons there. What do the colors mean?
Well, it's color-coded by the intensity, by how bright in gamma rays it is. But I should point out that the disk here, they've actually subtracted off the contribution from the disk, because the disk is glowing in gamma rays much brighter than the Fermi bubbles and the smaller.
So in order to see it at all, you have to subtract all that out.
They have to subtract off the disk, and that is actually quite a complicated process. They have to model how much it is. So this is a cleaned up map that you're seeing right here, which brings out the size of those Fermi bubbles.
Is that why those black areas there? Did that come out of in the subtraction?
That's right. Yes.
Okay. All right.
Exactly.
So you subtracted out the contribution of the disk because it's so bright in gamma rays that you can't see these lobes. Now you can see the lobes and what we have to join us. So you've made some pretty interesting measurements for us using Hubble. You have pointed it at a quasar that just so happened to be in a good spot to measure these very strange things that I guess only recently have been discovered. These features of our galaxy, these strange kind of lobe things, correct?
That is right. In fact, these lobes called the Fermi bubbles were only discovered in 2010 in their gamma ray emission by a satellite the that NASA operates called the Fermi satellite. So really only in the last 5 years have we known about this new component of our galaxy, and we were able to use Hubble to measure how fast the gas was moving into these lobes, what that gas is composed of in terms of its chemical elements. And this was the first time we'd able to really nail down some of these properties of the gas.
It's awesome, and I want to get to those measurements in just a minute. But Scott, can you put up that diagram that shows the Fermi bubbles? Fermi bubbles. Sorry. All right, so here's what they look like, or at least this is an artist impression of what they look like, correct?
That is right. So what you can see here is the disk of our Milky Way. This is a side-on view of what our galaxy would look like from someone sitting outside. The disk of the galaxy comes across at a diagonal there, and those two purple lobes are centered on the core of the galaxy, the center of the Milky Way. You can see there is a lot of emission along the base of the lobes as you get closest to the center of the galaxy. And these things, they're really emitting light all...
We can see kind of a little map of an all-sky map of the and gamma rays. Are these other features like the ones that are like in the upper right part of the lobe there? Is that part of our galaxy, or is that background sky? Is that part of the lobes? How do you know?
Well, it's very hard to know, and actually, that's an open question. As you go up into the northern Fermi bubble, you keep going to the north. You do see that orangey region, and that some of that may be associated physically with the Fermi bubbles, but some of it could be in the foreground. I mean, there are spiral arms of our galaxy between us and the galactic center, and those spiral arms can blow up material. They can blow gas into the halo, which can also end up giving you X-ray emission and gamma ray emission. So it's actually very hard to tell from a map like this what is very close to the galactic center and what is somewhere else. But as we'll get into, that's where the Hubble data is actually very useful, because Hubble is able to look at this from a different perspective, from a different angle, with its different types of data, and that can give you more information about where things are.
So based on this image, all we know is where it's bright and gamma rays. We don't know how far away it is, or where, any location information.
You got it, exactly. All this is total intensity. So it's you've got to be careful with this alone, what you really understand and what you don't.
Okay, you also took we also have images in other wavelengths, don't we?
That's correct.
Wait. So I have a question. So that loopy thing off to the left, what are those loopy things? Have you figured out what those loops